Welcome, friends. Let's solve exponentially. Yay, can't wait. Right? Okay. So what's a logarithm? Exponent. It's an inverse of an exponential function. An exponent. Logarithms are exponents. So when do we use them? We can figure it out after today's lesson, right? That's when we are going to use logarithms. We're going to use them today. Okay. First thing I want to do is I want to show you guys this cool video. All right? Yes, you may. All right, check this out. I'm going to pause the video at one point and kind of explain a little bit.
The ratio of a circle's circumference to its diameter. But
first of all, did you guys know that?
An equally fundamental number known to any...
The ratio of a circle's diameter and circumference is pi. Did you know that? It's kind of cool, right? So if you go all the way around the world, I do not. No, I don't. Okay. So if you measure all the way around the world and then you were to be able to go right straight through the Earth, right, you get 3.14. So that's pi. No, we're going right through the Earth.
We made a video about pi, the ratio of a circle's circumference to its diameter. But there's a less famous but equally fundamental number known to anyone who's taken high school algebra. It's about 2.71828182845945, and so on. And it was first defined by Jacob Bernoulli, but later Leonhard Euler called it E, and the name stuck. Bernoulli first defined E through compound interest. Now, compound interest says that you get a little bit of money in interest every period, and that money you gained helps you gain even more interest next period. In other words, your interest compounds. So, if you stick $1 into a bank account with 100% interest rate compounded annually, you'll get $2 at the end of the year. If it's compounded semi-annually, you'll end up with $2.25. Quarterly, and you'll end up with $2.44. Monthly, $2.61. Weekly, $2.69. See where we're going?
So I think he says that really, really fast. Okay? So if you get 100% interest on $1, you have $2. But if you decide to break that up semi-annually, after 6 months you get the $2, and then you take interest on that, right? Let's take it back. $2.25. And if you take the interest, now if you decided you were going to do it quarterly, where does he take us back to that? Quarterly is every 3 months, right? Then monthly, then daily, then hourly, then per second. Like if you were to do it continuously, like it just keeps going on itself, that number is never going to get bigger.
Weekly, $2.69.
E.
See where we're going? If you increase the number of compounding periods a year towards infinity, then you'll get closer and closer to E dollars. In statistics, it describes the most important statistical distribution, the normal. In biology, it models populations of species through the logistic function. In physics, E describes the exponential decay of a radioactive material.
I've seen that.
So, while E may not be as famous as pi, it's easily as fundamental and immensely important.
Okay.
The number pi is equal to 3.141592653, and so on and so on.
Okay. So kind of cool video, right? Yes, Christian. Because the number just, because the amount, like if you were to compound, the number got big at first, right? But then it got bigger by very small amounts because the number it was so small, right? So as a fraction, So if we take a fraction of fraction, it gets even smaller, and it gets even smaller, and it gets even smaller. So that's why it just keeps going and going and going and going and going and doesn't stop. E forever. What? We'll look at it again, okay? This isn't the only time you're going to see that diagram about money like that. We're going to look at it later on this week. Okay, so we'll talk about it further then. All right, but I didn't want to get away from this lesson without at least introducing what the idea of E is. So, today, recall that this graph here, can you tell me what the base is just based on looking at the graph? Well, 0, 1 is its reference point, that's for sure. But there's something else that can tell you what the base is. Base is 2. How do we know the base is 2? Well, we don't really call it the slope, but I get where you're going with that one. So if I put in for x, if I put 1 in for x, 2 to the 1 is 2. So when I go over 1, I go up 2. That's how I know the base is 2. If I put in 2 to the second, I'm going to get 4. So when x is 2, I get 4. So now the dashed line is the inverse of that. That's the logarithmic function. So it also has a base of 2. It has to, right? Now look at this one over here. This one, if I put in 1, I get 1, 2, something. So what do you think this base is? E. Right? So what do you think the inverse of it is? Log E, but I told you E got its own log, right? It's called ln, natural log. Now you know why E gets its own name, right? Because it's that special. Caitlin, go get a drink of water or something, because you need to be watching this today. Okay, so let's use that. Compare and contrast them. I haven't heard a magic number yet. I should hear 3, right? Why should I hear 3? Fidel, why 3? Because 2 to the 3 equals 8. Just by looking at it, you guys should be able to say, well, Mrs. Muller, of course 3, because 2 to the 3 equals 8. Yeah, that's true. Let's look at how we've been doing it in a fancy sense. We've been saying, if I'm trying to solve for an exponent, I need to find a common base. The common base in 8 would be 2, and to the exponent 3 would give me an 8. If I have common bases, I can compare exponents. So this problem now turns into x equals 3. All right? Because we're not always going to be able to just look at something and go, oh, the answer, that's 3. So that's the process of how we would solve that. Now here's another problem. Can you tell me what x equals here? It's 3 plus 1. I'm not sure. I'm not so sure about that. No, we can't add stuff. We got to be able to solve it today. So what do you think we're going to use? Logarithm. We're going to use logs. Okay. Excited? All right. I felt like when I came to this screen, everybody freaked out on me last period. So let's back up the screen and do something like this. So what is, let's see, remember the B box. So What does this equal? What does this equal? Right? What does this equal? What does this equal? Zero. Okay? Matthew. So, I don't know how much I can express. You guys need to be paying attention to this. Okay. Let's change this into logs. Okay? So in order to change this into logs, I would say log base 3 to the 27 equals 3. And log base 2 to the 16 equals 4. And log base 5 to the 25 equals, and log base 5 to the 1 equals 0. Alright, so those are comparable. You guys saw in your puzzle, you saw stuff like this. Log base 5 to the 5 squared equals 2. You guys had a hard time with those. I was trying to help you. Whenever something is hard on, always turn it back into exponential. 5, so I would say, when I'm just looking at this, I would say 5 to the what makes 5 squared? 5 to the 2. That's why the answer to this is 2. One more? I know. Well, we're going to make them less confusing today. What about log 6 to the 6, 3? What does that equal? That equals, so 6 to the what makes 6 to the 3? 3. Kind of. So this first property, so b to the what makes b to the x? X. Correct? Now let's put it in log form. B to the what makes b to the x? X. Here's your first property. When your base and the number are the same, it just equals the number. I mean, it just equals the exponent. Okay? So let's play with that a little bit. So it's always going to be true. So if I have log 5 to the 5 to the 2, I have just 2. Log 7 to the 7 to the x equals x. What's the hard part? Oh, we're getting there. It's not, none of it's hard. It's just new. Okay? But it's a lot of new, all at once. We got to put it all together. Okay, so I feel like I can go on from here. Next property. Anything that gives me a 1 is 0. So it doesn't matter whether it's a b or a 5 or 100 or 1,000. It always is, the exponent has to be 0. That one you guys already pretty much know, right? Finally, not finally, because I do have one more after this. Anything to itself is 1, right? Because what I'm really saying is there's an exponent of 1 here, and I'm just canceling it. Okay? So far, so good? Okay. Next. Do you remember this property? Power to a power property. Okay, this is the problem. This is why we're revisiting this. Matthew. Okay. M to the n equals m times n. You can't combine them. We're multiplying them. This is, what's the most common error with this? Adding them. 2 to the 3 to the 3 is not 2 to the 6. 2 to the 3 times 2 to the 3 makes 2 to the 6. Because this is 3 2's and another 3 2's, which makes a total of 6 2's, right? Couldn't have said it better myself, Amadeus. 2 cubed is 2 cubed times 2 cubed times 2 cubed, correct? Which makes 2 to the 9th. So you could say it, that's the right way. So if you were to explain that, we could explain it by saying, I'm multiplying 2 to the 3rd 3 times itself, right? We're doing it 3 times itself. That's going to be super important right now. All right? Caitlin, look it up. All right, so if everybody agrees with that, let me just cover this up, and let's talk about power to a power when it's a log. Let me just, power to a power when it's a log. Logarithms are what? Exponents. So if I were to say base 2, I get 3 to the 3rd power, I'm really saying this right here 3 times itself. Does that make sense? I'm saying log, what that is saying right now is log 2 to the 3 times itself. So my new property, the most important property you will see today, ever with logs, it's so used. Whenever there's an exponent out there in front of or above a log, it really means 3 times itself. Okay. I'm going to show you. Okay? I'm going to show you. Whatever the answer is to this, it's 3 times that. Okay? All right. Does that make sense since logs are exponents? Okay. It's like I'm multiplying the exponent. Okay. So, let's recall. Let's try with another example. So, recall, what is b to the bx? X, correct? Good. So, if I were to do this problem, you would tell me the answer is 3. Now let's use the last property that we have. Instead of, that's the property I already told you, right? But let's use the property of, I'm going to pull that 3 out in front. So now I have 3 times log base 2 to the 2. Well, isn't 2 to the 2? No. It's 1, right? Because there's a 1 right there? Because 2 to the 1 makes 2. So isn't this really 3 times 1, which equals 3? What? The multiplication part's harder?
No.
Okay, so now we're going to use it all. That's all we need, and that's what we're going to use. So here's my power to a power property with logs. When I have m to the n, I just multiply my exponents. But now that I have logarithms, I bring the exponent out front and say it's being multiplied n times. Okay? We good? All right. I'll put this on a poster as well. That's just the answer. Yes. Okay. There's the proof for it, which I'm not going to go through. Pretty complicated, but you end up right there. All right? If you're interested, we can look at it later. Okay? I'm gonna show you right now. So let's go ahead and use it. So can you describe to your partner what this rule is? What did you guys come up with? Share? Anybody want to share? What's the rule? Make it up in your own words. What do you want the rule to be? Nobody wants to share. Oh, the back of the bus to the front. I like it. Back of the bus comes out in front. Top of the bus comes out in front. I like it even better. Top of the bus moves it out in front. I know, because if it's on the top of the bus, it could fall off. So we might as well put it out in front. That one's even better. I like it. Okay. So same thing with natural log. If you see a natural log that's raised to an exponent, you can turn it into multiplication. Okay? All right. So to be or not to be, now we're going to call it, this is what you're going to say to yourself over and over again. To log or not to log. That is today's lesson. Okay? To log or not to log. You ready? Okay. You're so scared. Okay, can you take a guess? To log or not to log? Not to log. Why? That shouldn't be your answer. You're going to say, Mrs. Mahler, I already see something common with these two. They have the same bases. So not to log. Okay? So this, you guys should recognize this. It would be 5 to the x minus 3, and I'm going to substitute in 5 to the second. Common bases so I can compare exponents. So this problem turns into this, which is very easy to solve. Right? Okay, next one. Log or not to log? Log. Why? They don't have common bases. So here's your steps. This one's a very simple one. They're not going to be this simple. So you're going to ask yourself log or not to log, right? So you're going to want to isolate your bases on each side. Ask yourself, do they have the same bases? If they do, you set your exponents equal. So if the same bases are not possible, we have to use a log or an ln on both sides. So what I'm going to do is this is a property of equality. If I do it to one side, I have to do it to the other, right? I can multiply that by 1,000,000. But I have to make sure I multiply the other side by 1,000,000, then they're still equal. So I'm going to put a log out in front of both of these. So log, let's change it. I'm going to put a log. I'm going to throw a log out in front. So it's going to be log 5 to the x equals log 52. Now what bases do those logs have? Nope. 10. They have a base of 10. If I don't put anything, it's the default. If I don't put anything, the default is 10. It's a base of 10. Reason? That's what's on your calculator, a base of 10. So now, what can I do? How can I take off the 10? Put the x out front. It's on the top of the bus, so it needs to be pulled out in front. Okay? Right? That's our whole reason for logging both sides, so that we can make that exponent come out of the air. That's our whole reason for using logs. So now I have x times log 5 equals log 52. So how can I get x all by itself? No, what's the inverse of multiplication? Division. Everybody get a calculator out. I do not have enough calculators anymore. They have dwindled throughout the year. Didn't I tell you that was going to happen? So the problem is if you don't get here early on test day, you may not have a calculator to use. Do you think you're going to need a calculator? Yeah, you're going to need a calculator. So put this in a calculator and let's make sure we all get the same answer. I want to back up and just say one small thing. I'm wondering if anybody saw this. Let's see, right here. I'm wondering if anybody saw this. Hold on a second. Did anybody see that I could have done this? I could have been very strategic on what I logged both sides by. Right? Could I have done that? I could. Why would I do that? That cancels. So now I have x equals log 5 to the 52. But most of your calculators won't do that, but there is another thing you can do with this. But I wanted to, I just didn't know if anybody saw it or not. Hold on. Okay, so I want to make sure. What did you guys got? Let me put it in my calculator. You're going to get, when we use logarithms, and the reason we do this, we usually go to the 3 decimal places because they're so precise, right? We're trying to find very, very small numbers. So x is about 2.455 is what you should have gotten. What, Robert? Log 52 end parenthesis divided by log 5 end parenthesis. Okay, so half of you are probably not putting this in a calculator, which is not a smart idea, because you've got to be able to know that you can put this in a calculator correctly, because you're not going to be able to guess. Yes. On a calculator. You're not going to be able to use a phone on a test. Yes. Yes. Let's do this. Okay, so I'm going to put in log. Do you see that I get log parenthesis, log 52, end parenthesis. That's super important. You have to put the parentheses. Divided by log again, 5, end parenthesis, equals 2.455. Yes. Yes. Okay. All right. What I'm doing is I'm taking an exponent and I'm dividing it by an exponent. right? What was the original problem? 5x to the 52. Is it reasonable? 2.45. Well, 5 squared would be 25. 5 cubed is 125. So would 5 to the 2.455 get you 52? It kind of makes sense, right? Yes. You only do that if you're looking for, yes, you're looking for an exponent that's a variable, exactly. All right, I'm going to do 2 more, and you can see why these are going to get a little bit more difficult. All right, so what do I do before I even decide log or not to log? I need to move that 1 over. So when I move the 1 over, I get 2 to the 5x minus 1 equals 16. Log or not to log? Why? They have something in common. They have common bases. So 2 to the 5x minus 1 can be compared to 2 to the 4. And now it's a simple problem that you can solve. What about this one? To log or not to log? Log. We're going to log this one. I have log 2 to the x squared minus 3 equals log 15. Why in the world would I do that? So that I could move the exponent off the top of the bus out in front and multiply. So this is now, I can, but we can't do that. I haven't shown you how to do that yet. Okay? So I I want to make sure all of this is the exponent, so it's all being multiplied. So it's x squared minus 3 times log 2 equals log 15. Now what? I want to get x by itself. What's the next thing? Divide the log. So divide this by log 2 and this by log 2. Now, the next thing you guys are going to do, the mistake you're going to make, is if it's log 15 over log 5, what do you think people are going to do? Log 10, no. Guys, hold on. If this did come up, what would somebody do? They would divide 5 by 15. Correct? That's not correct. Okay? This is an exponent divided by an exponent. So that would not cancel and give you log 3. That's going to be the most common error that you guys make. Okay? All right. So now I have x squared minus 3 equals log 15 over log 2. Now what do you think you would do? You would add 3 to both sides. So now I have x squared equals, guys, over log 2 plus 3. Now what would you do? Square root the whole thing. Right? So now I would have x equals the square root of log 15 divided by log 2 plus 3. But was it all that difficult? It's not really difficult. It's just different. Let's put it in a calculator. Make sure you guys can do that. So I do second the square root. Parentheses are going to be your friend on this one. Let's see the problem. Okay. So we have square root. Then I'm going to put another parenthesis in there because I'm doing a division problem first. So you've got square root parenthesis. I'm going to put in another parenthesis. Then I'm going to throw those logs in there. Log 15 and parenthesis divided by log 2 and parenthesis. Hold on. Then I'm going to end that parenthesis. Does that make sense?
Yeah.
I just finished the division part, and now I'm going to add 3, but now all of that's under square root, so now I need to close the parenthesis one more time. I'll write that on the board too. So you should have gotten 2.628. Yes, parentheses are your friend. 2.628. I'm going to show you right now. I'll show you again. 2.628, is that what I said? 2.628. Okay, this is how I got this answer right here. I put a square root. When you put the square root, it automatically puts a parenthesis. I put log, it gives you a parenthesis. You put 15 in, you close the parenthesis. Divided by log, it's going to give you a parenthesis. You put a 2 in, you have to close the parenthesis. Then you close it again because that's your division problem. Then you have to add 3, and then another parenthesis to close the square root. Yes. Then you can equal it. Then you put it in a wrong. That's why we're practicing it. Right? I think that's good enough right there. No, there'll be exponents on there too, and graphing. All right, I think that's it for now.